Okay, welcome everybody to the ISI colloquium. We are very happy to have Turgay Bayraktar from Sabanci University from Turkey. So he has agreed to us. Thanks to him for agreeing to give a talk online. So he will be speaking about universality principles for random polynomials. And the slides are posted online. I will be posting the link again. And if anybody has questions, you can either unmute yourself and ask, or please post it on the chat. I will interrupt Turgay and ask him. Over to you, Turgay.
Thank you very much for the introduction and the invitation. It's a pleasure. So today I will talk about zeros of random polynomials and some universality principles about them. So in order to motivate our task here, I will start with this basic model. It's been studied extensively and known as a Koch ensemble. So a Koch polynomial on the complex plane is given as just like ordinary polynomial, where these coefficients aj's are either real or complex random variables, which are identically distributed, at least in this talk, and independent. So they're IID, and their common distribution is denoted by this P here. Now, I will describe how you put a probability measure on the complex vector space of polynomials of degree n. So you identify the polynomial with its coefficients. Now, these are some complex numbers. Well, okay, they're random variables, but if you identify a deterministic polynomial with its coefficients, you get a vector in Cn plus 1, where n is the degree. Now, as these are random variables, they have this common distribution P. So you endow this Cn plus 1 with the product probability measure coming from these random variables aj. And then you pull it back to the space of polynomials under this identification. So that allows you to put a probability measure on the space of polynomials. So this is your probability space here. Of course, you can do this for each degree, and that allows you to define this product probability space where n runs over all degrees. Now, the elements of this product probability space are sequences of random polynomials. Now, we're interested in zeros of random polynomials. So we can factorize a polynomial like this, where an is the leading coefficient and zeta j's are the roots of fn. And then define a measure valued random variable. So you take the polynomial fn, and then you put a point mass on each zero of it. And then you get this measure of total mass equal to n. And so you can talk about expected value of this random variable. Of course, it's going to be a measure valued object. So in order to define it, so you take a continuous function with compact support, in other words, a test function on the complex plane. And then the action of this measure on this function will be, you basically act by these measures. So these are your random measures on phi, which is just evaluating the sum of the values of phi at the zeros of random polynomial. And then you take an average with respect to this prob n on the space of polynomials. So this is your expected zero measure. And we are interested in asymptotic distribution of this object. Of course, as you see, the mass of it depends on n. So if you divide, it'll be a probability measure. So we're interested in the asymptotic behavior of 1 over n expected zfn, or 1 over n zfn. So we're interested in these objects. And there's a classical result that goes back to Koch in the case of when AJs are IID real Gaussian. Later on, Hammersley studied the complex case, and Schaap and Van der Bey gave some more information on the rate of convergence. So what the theorem says, that AJs are IID complex or real valued Gaussian random variables of mean 0 and variance 1. So you have the standard case, okay? Then actually this last condition doesn't have any importance, but just to reflect the original theorem. Then the normalized expected 0 measure is asymptotic to the normalized arc length measure on the unit circle as n goes to infinity. So this convergence here in the weak sense, in other words, in the sense of convergence of measures. And also almost surely the normalized 0 measures supported on the zeros of random polynomials. So here almost surely means that for almost every sequence of random polynomials, this measure converges to the same normalized arc length measure on the unit circle as n goes to infinity. Now, I want to illustrate this result by using some computer pictures. So basically what I do, so this is a simple code written in Mathematica. So it says that choose some random numbers AJ with respect to, I think this is complex Gaussian here. So form your polynomial and plot the zeros of that polynomial. Here, the number 10 refers to degree. And so of course, this picture is a 2 by 2 square on the complex plane. Some zeros may fall outside the square. So you only see the ones inside the square. So it shows a random polynomial of degree 10 and plot the zeros. And then as the degree increases, fairly quickly, what you see is that the zeros are accumulating around the unit circle. Okay, so that's the illustration of this theorem. Okay. Now, why is this happening? That's the question. So here's one approach. So the monomials ZJ form an orthonormal basis with respect to this inner product, which is defined with respect to this arc length measure. And then you can consider the L2 space with respect to the same measure on the circle. And if you look at the orthogonal projection from the L2 space to polynomials, that projection has an integral kernel, which is called the Bergman kernel, which is given here. It's finite dimensional Hilbert space theory tells you that the Bergman kernel is given by basically in terms of the orthonormal basis, like this. And it is also the reproducing kernel of the point evaluation at the point Z. That means that for any polynomial, you have this, okay? Now, well, if you restrict the Bergman kernel on the diagonal, okay, so it's a geometric series, you know how to write this in terms of the geometric series. As long as mod Z is not equal to 1, you have this. If mod Z is equal to 1, you just add 1 and plus 1 times, so you get this. Now, if you look at this expression, so log of the Bergman kernel divided by 1 over 2n, you will see that this has been known. Analysis is classical that this function here converges to log plus, which is the maximum of log mod Z and 0. It's the positive part of the logarithm. And this convergence is locally uniform on the complex plane. And then once you have this nice convergence in the correct topology, you can pass the Laplacian of the left-hand side, and Laplacian of the right-hand side. So this implies that the Laplacian of this, in the sense of distributions, converges to Laplacian of this one, which is this. Okay. Well, I think you need a normalization here because I got 1 over p. Okay. So this basically tells you now that, okay, so take your polynomial fn. So think about your polynomial as an inner product. So you have the coefficients in Cn, and you have this vector given by the monomials. But you divide the monomials by the sum of the squares. In other words, the norm of it. This is just Hermitian norm, the Euclidean norm. So if you divide and multiply, and this extra term pops up, and then you get this expression plus this. Now you have some information about this coming from the previous line, and then you need to understand how to control this one. And this is the place where you use probability, because you divided the norm of this vector 1 z squared z cubed, etc. This is a unit vector here. Now you use some probability, like just some sort of Borel-Cantelli type of argument here, to show that this actually goes to 0. This term here goes to 0 in the correct topology. So you need, because eventually you will pass to Laplacians, and the Laplacian of this object is nothing but the 1 over n times the 0 measure of Fn. So Laplacian of this one converges to the correct object. So all you need to show that this one goes to 0 in the correct topology. And there you use some probability and some potential theory. So you have these these are differences of subharmonic functions. You use some sort of Hartogs lemma from potential theory that basically allows you to show that this term goes to 0 in the correct topology, therefore the result. So this was the argument for the Kutch ensemble, but it seems like it's a quite general argument. As long as you have a nice inner product and a nice basis, as long as you have information about the Bergman kernel, this kind of an argument would work. So let's generalize, or at least state a generalization of the Kutch theorem first. This was a recent result by Ibragimov and Zaporizet. I think it was in 2013. This was kind of a universality result in terms of the coefficients. So what it says that if the coefficients Aj are non-degenerate, so basically non-constant, IID random variables with the following moment condition, so they have finite logarithmic moment, then, in fact, this was a necessary and sufficient condition for the zeros converge to the normalized arc length measure almost surely. Okay, so for almost every sequence of random polynomials, you have the same sort of convergence. So I basically illustrated some pictures which are similar to the previous experiment for different families, and these are, I think, F2000. So computer chosen a random polynomial with respect to a standard Gaussian, uniform, or Bernoulli distribution. This is the case where AJs are plus or minus 1 with probability 1/2, and then just plot the zeros. Later on, I will say a few more words about the similarity of these pictures. Okay, now another ensemble you can work with is the elliptic polynomial, where you use a different orthonormal basis. So the orthonormal basis in the Kutch ensemble was just monomials. Here you have the scaled monomials. I'll tell you what the inner product in a minute, I believe. But the picture here this time is quite different than the previous one. So you have, in this case, the zeros of random polynomials of this form are equidistributed with respect to the normalized. So this is the Fubini-Studi measure on the Riemann sphere. Okay. The third model I wanted to illustrate is this Weil polynomials. They are of this form, where again, AJs are IID random variables. You again have the scaled random polynomials like this, so scaled monomials like this, and then you look at random linear combinations. This time, zeros are equidistributed with respect to the Lebesgue measure supported on the unit disk. So the picture, this time, the picture pops up like this. Okay. Now, why these three models are emphasized, maybe I should say a few words about that. Well, there is, the random matrix theory has been well established, comparable to this model here, where you study the asymptotic distribution of eigenvalues of random matrices. Now, in this model here, the zeros of random polynomials of this form behave like, you will remember this picture from distribution of eigenvalues of Gaussian unitary matrices, right? And the first one, the Koch ensemble, was looking like the circular law. So that was the Gaussian orthogonal matrices. So there is a similarity. And as also well known that in order to study asymptotic distribution of eigenvalues of random matrices, people use potential theory. So there's a connection between asymptotic distribution of random eigenvalues of random matrices and the potential theory. So it's the same here. This time, so I will introduce the necessary background on the potential theory that we will use here. So you have a closed set and the complex plane K, and then you're assuming that this set is not small in the sense of potential theory. That means that it has positive logarithmic capacity. And phi is a weight function. For now, we just take a continuous function. And we look at this following energy problem. So we have this energy function, which is defined on the measures nu, which live on the set K. And we look for the minimizer of this energy function. And there's a theorem in potential theory, and it says that under these assumptions, there's a unique minimizer, nu K phi, and we are looking for its logarithmic potential. Okay, I'm actually speaking some details here. There should be a constant here, but that's not a problem for the moment. For those who know potential theory, that if you want to write down the green function, you take the logarithmic potential and add a constant. But for now, we don't emphasize that. Now, this measure nu K phi is called the weighted equilibrium measure associated with K and phi. And the green function is a function which is subharmonic on the complex plane, and that is harmonic outside K, and grows like log at infinity. Okay, and there is one technical assumption here that this K is a regular set in the sense of potential theory, so that this function Vk phi is continuous. In most cases, for nice Ks like interval, circle, etc., that's the case. Okay, now the inner product in this case will be on the polynomials, will be of this kind. So you take f and g bar. Now you have a weight here, and you integrate with respect to this weighted equilibrium measure. So this allows you to choose an orthonormal basis for the set of polynomials. Here, I just assume that K is a closed set. So in general, you need to be careful here. Not all polynomials are integrable, but at least for the three models we discussed, I will tell you in a minute that that's the case. And then you fix an orthonormal basis, and then you look at random linear combinations. Okay, so because the dimension is n+1, you have n+1 such polynomials, and then you write down the Bergman kernel like this, and you come up this general picture. For instance, in the first example, the Koch ensemble, your K was just the unit circle. Your weight function was identically 0, and the equilibrium measure was normalized arc length measure. In the second ensemble, your K was the complex plane, phi was 1/2 the log 1 plus mod z squared, so that all polynomials are L2 integrable, and because this that allows that. And the corresponding measure was just the asymptotic distribution of zeros of random polynomials. Similarly, for the Y ensemble, K was the Hall complex plane. Again, phi was mod z squared over 2. And for this pair, the weighted equilibrium measure is, again, the asymptotic distribution of the zeros of random polynomials. So the theorem, in summary, for these models, zeros of random polynomials that are random linear combinations of orthonormal polynomials, as I described in the previous slide, is asymptotic to the weighted equilibrium measure nu k phi. Now, the idea is to generalize this picture to several complex variables. Okay. So let us motivate.
One question.
Yeah.
So when you say in the asymptotic distribution, it's somehow the empirical distribution. So there is a small fraction or some vanishing fraction, could be zeros, could be very far away or even very close to origin.
Exactly. When you divide by n, yeah. So it's just like, right, just like here, like when you divide in the theorem, when you divide by n, right here. So that basically tells you that the convergence is in the sense of measures. So of course you can expect that some zeros staying are away from the support of the equilibrium measure, but the number of them are very small compared to n.
Is anything known about this kind of where is the largest possible, the zero, the farthest?
I think there are some papers for zeros of Koch polynomials. For the general case, I'm not sure.
Okay.
Yeah.
Thanks.
Mm-hmm. Okay, so let's come back to where we left. So let us try to motivate this universality principle. So there's a classical theorem from probability, right? The central limit theorem for the IID random variable Zj of mean 0 and variance 1. You look at this normalized sums. You know that this thing converges in distribution to the Gaussian. And this does not depend on the distribution of Zj. So this is kind of a universality result here because the limiting object is and does not depend on Zj or nature of Zj's. Here, the asymptotic distribution of suitably normalized zeros of random polynomials when you divide by n is independent of the choice of the probability law defined on the random polynomials, if you remember this theorem of Ibragimov and Zaporizhit. So that's kind of a global universality result because the limiting object does not depend on the probability law of the coefficients. And another universality principle we might expect if you suitably normalize the linear statistics. This will I will introduce these at the end of the zeros of, but this time Gaussian random polynomials. We will show that that is also asymptotic to the Gaussian. So this this second universality principle is independent of the choice of the weight function. So the idea here is that you change the geometry, but still you get the same limit at the end. And that's why it's called geometric universality. Okay, so I will explain these things in terms of multivariable polynomials. Okay, so in the multivariable case, potential theory is replaced by some other context, which is called the pluripotential theory. There, in the potential theory, you work with subharmonic functions. Here, you work with plurisubharmonic functions. So let me not go into details, but tell you that a plurisubharmonic function is an upper semi-continuous function that is subharmonic in every complex direction. And here, we define the Lalonde class, which are plurisubharmonic functions that grow at most like the logarithm at infinity. Okay. For instance, if you have a polynomial, log mod pz divided by the degree is a Lalonde class function. Okay. Now here, let K be a set which is not so small. That means here non-prepolar in terms of this pluripotential theory. And again, we are taking a continuous weight function in order to define our inner product, like in the one variable case. Now, there is a version of vk phi and several complex variables. This thing is called global weighted extremal function. That is the upper envelope of all Lalonde class plurisubharmonic functions that are dominated by the continuous weight function phi on k. Okay. So this is going to be our potential in this case. If we were in dimension 1, this would be precisely the same function k phi we defined earlier. And the Laplacian of this would be precisely our measure. But now we are in higher dimensions. So in m-dimensional case, we need an operator which gives you a measure by using this function. So this operator is called the complex Monge-Ampère operator. Well, there is a theorem which says that if you have a function that is locally, pre-subharmonic function that is locally bounded, in this case, we are taking a nice k and nice phi so that vk phi is continuous. For instance, you can take your k to be torus or the sphere in the complex Cm, so that these assumptions are, and phi to be 0, and these assumptions to be satisfied. Now you can define the measure nu k phi as basically this object here. So these are forms which has distribution coefficients, and then in distribution theory there is so this thing makes sense and defines when you wedge m of them, that defines a probability measure. In dimension 1, this thing coincides with the normalized Laplacian. So I'm just doing the same thing, except that in higher dimensions, I use the complex Monge-Ampère in place of the Laplacian. Okay, so for example here, if your k to be the torus and phi just a 0 function, then you get the normalized product of the arc length measures in each argument. Okay. So this is the case when we work with the Kach ensemble. Or you can use the unit ball, okay, so the sphere, so to speak, in place of this. Then for this case and phi to be 0, then for this case, this nu k turns out to be the surface area measure on the unit sphere. So even if you start with the ball, you end up with the surface area measure on the sphere. And finally, if you choose your k to be all of Cm and phi to be 1/2 log 1 plus mod z square, so you see this is the potential. If you take this thing and calculate its Monge-Ampère, this gives you this Fubini Studi measure. Sorry about that. Some of it is just here, but I think it's some dz constant times 1 plus mod z square over m plus 1, dimension plus 1. So this is the higher dimensional analog of this the elliptic ensemble. Okay, so it seems like this is the right setting because we have the generalizations of all the one-dimensional objects. And now it's time to define our inner product in the same manner. So now we have multi-variable polynomials here. We are integrating this product over k again with respect to this, this measure now. This is the weighted equilibrium measure. And don't forget that in higher dimensions, the dimension of the space of polynomials is given by this here. So n plus m chooses m. M is the number of variables. Capital N is the degree, the total degree. And a random polynomial is, once you choose your orthonormal basis, a random polynomial is of the form here, like in the previous case, is just the random linear combinations of these orthonormal polynomials. So one remark here that I'm just assuming the AJs are again IID complex or real valued random variables. But of course, if you choose a different orthonormal basis for arbitrary choice of AJs, your probability space change. But if you work with, say, Gaussians, say complex Gaussians, because complex Gaussians are unitary invariant, it doesn't matter which orthonormal basis you choose here. So for certain ensembles, the choice of orthonormal basis affects the choice of the probability measure. Okay. But in higher dimensions, I'm assuming that my probability, well, my random variables have a probability distribution that is absolutely continuous. Why do I need this? Well, because in higher dimensions, when I choose random polynomials, say in dimension 2, I have two random polynomials, f and g. So I look at their zero locuses. Now they are divisors. They're not discrete. And when I look at the common zeros of random polynomials, I want these divisors to intersect properly so that when I choose a top system, the common zeros become a discrete set. So I need this kind of a condition to ensure that. So this uses, I don't know, either Sard's theorem or some other theorem from geometry, algebraic geometry, that for coefficients in general position, the zero locuses of top degree system, say F1 through Fm, intersect properly and give you a discrete set. And the number of elements in that discrete set is n to the m. And that's known as Bézout's theorem. Okay. So as in the univariate case, we now put a probability measure on the space. How do we do this? We again identify the polynomial with its coefficients. Now we are in CDN, and then we put the product probability measure on CDN and pull it back by this identification again. And so this is I just explained. So the Bézout's theorem tells you that when the coefficients are in general positions, if you take a top system, so M is the dimension here, this system has d to the m zeros and n to the m, so n is the degree, n to the m zeros, and the normalized zero measure is given by basically this. Now, of course, Bézout's theorem with the previous setting, so here, Bézout's theorem tells you that for almost every choice of F1 through Fm, you will have a discrete zero locus, but it doesn't tell you where they are or how they are distributed. It just tells you a number of them. And so what we want to do, we want to localize this result. And the way we want to do it is that, so when I look at a small ball in the complex plane, I want to know how many zeros lie in the small ball, right? So, of course, I can't tell this for every system because you can just reverse the problem and construct systems which does not have any zeros in this ball or all zeros in the ball. So I want to say something for generic systems. But this generic here, just not like in the Bézout's theorem, because it was just like saying that in general position, that means that the coefficients, if you think of coefficients are just vectors in CDN, okay, dn is the dimension of the space of polynomials. So, so in general position means that away from a hypersurface. Now here, for me, generic or typical means that random. So I will convert this term generic to random and try to localize this theorem here. Okay.
Turgay,
yeah.
Two questions. One is, what does it mean when there is a superscript? How do, I mean, just a notational thing. When you say Fn superscript 1 to n.
Oh, okay. So, sorry about this. I'm sorry. So this is, so you choose a system. So you're in C, so all these polynomials are over Cm, okay? And then you choose a top system. So when the system in general position, the common zero, the simultaneous zeros of these polynomials form a discrete set. And this Z F1 through Fm is that discrete set.
Okay. So is each, I mean, you had a Fn in the previous slide. So each Fn1 is a copy or is it like a, I mean, you are taking independent copies of this form or different?
Exactly. Yes, it's a good question. So, so I have a probability measure on the space of polynomials of degree n. I choose a random polynomial, let's say f1, and independently f2, etc. fm. So these are all chosen independently. And then now this form a top system. And then I look at the simultaneous zero locus of this top system. So I denote it by, let's say, z f1 through fm. I know that for this condition, I have n to the m of them. So I divide to make it a probability measure.
Okay, thanks. Yeah. And,
Right.
and
Yeah.
one more question is on the potential theory for the several, I mean, in CM, when you did in C, you had this definition of mu k as a variational characterization.
Yeah, there is, there is an energy functional, Abun-Mabuchi functional, and that's the minimizer of that.
Okay, thanks.
Okay. Now we can state this theorem in higher dimensions. Okay, so what do we do? So we choose a compact set. Okay, this theorem has some generalizations, but I'm gonna state something in a sort of reflect the basic examples. So you have a compact set in CM, and you're assuming that this compact set has positive capacity, some capacity. It's not so small, and it is regular in the sense that when you have a continuous weight function phi, the function vk phi is continuous. So those are the assumption on your k, and all the three examples that I showed earlier fall into this category, and there are many examples falling into this category. Now you put some moment assumption on your coefficients. Remember, in one variable case, this global universality result, it was just a finite logarithmic moment assumption. Now here I'm assuming a bit more. I'm assuming that the probability of this disk, so to speak, decays like 1 over the dimension of the ambient space plus 1 plus epsilon, some positive number. So it's a bit bigger than m plus 1. Okay. So in dimension greater than 1, I need a bit stronger conditions in order to get the asymptotic distribution of common zeros of random polynomials. So what is the theorem? So again, if you choose these Fm, F1 through Fm independently of the same degree, and if you normalize it by just dividing the number of zeros, the expected distribution of the zeros of the system of random polynomials again converge to this, the weighted equilibrium measure in the weak topology. Moreover, for almost every sequence of systems of random polynomials, you have the same convergence. So you have this self-averaging property for the zeros of systems of random polynomials. Okay, so maybe at this point I can now explain why this gives you a localization of the Bézius theorem. Because what this tells you that if you choose an open set, a relatively compact open set in CM, and if you look at the number of zeros of your system, so this is your random system, and if you look at the simultaneous zeros in U, and of course normalize it, so what this tells you that this is asymptotic to the mass of the equilibrium measure in that open set. Okay, so that basically now tells you that for a typical system, in terms of this probability space, for a typical system, you expect to have this many zeros in that neighborhood. There's some history here, and then there are some. I'll tell you some generalizations of this. Okay, so I think this was done first by Schiffman and Zeldich for the elliptic ensemble in '99. In fact, their result was written in terms of this complex geometric setting for random holomorphic sections of line bundles. And later on for polynomials, Bloom, Schiffman, and Schiffman gave the unweighted case when phi is equal to 0. So this particular case was in 2016. Later on, we get some generalizations of this result for some other distributions, for some other settings, including the random holomorphic sections. There is a survey one can, I can refer to a survey. I think that appeared in 2000, maybe 18 or 19, including myself, Koman, Marinescu, and Hendrik, that basically sort of explains the current status of the subject. So for those who are interested in the recent development of the subject, you can take a look at that survey. And now I want to, so this was the global universality and localization of Bézieux's theorem in terms of zeros of systems of random polynomials. Now I want to move on to a geometric universality. So here, yeah.
Sorry to interrupt one point. The condition on AJ, if you take M as 1, you get a 2 plus epsilon, whereas the Ibragimov-Zapored's result is you need only 1 plus epsilon. You don't need a 2 plus epsilon, right?
Right. Their result in dimension 1 is stronger. I also assumed here that the AJs has continuous distributions. Okay. They don't, for instance, assume that because so yeah, in dimension 1 we can get stronger results. But in higher dimensions, we have some other problems that does not arise in dimension 1. Like we need to ensure that the zero locuses intersect properly. And also, we also need to, the proof of this theorem is using the theory of positive closed currents. And it's done by induction on the dimension. So I take one polynomial first, and then I take two polynomials, etc., to get the result in top degree. And yeah, that requires some estimates, and that's why this kind of a stronger condition arises. But as you pointed out, if you look at only dimension 1, yeah, this would give a weaker condition in terms of logarithmic moment.
Thanks.
Mm-hmm. Okay, let's give some examples. Like so the generalization of Koch ensemble would be, you would just take this torus, okay? Or either you can take K to be torus, or you can take K to be the polydisk. You end up with the same result. And then your phi here is 0. The equilibrium measure turns out to be this normalized product arc length measure. So that is supported on the torus. And then with respect to the corresponding inner product, your monomials become orthonormal. So this is the most probably naive example where you think of random polynomials where they are random linear combinations of multimonomials. So this is your ensemble now. And I think it's been known, I mean, it's been known for a long time. I don't know who proved it, but the zeros are equidistributed with respect to this measure here, nu k, for the systems of random polynomials. But this theorem added only, for Gaussians, this has been known, but this theorem here added the global universality. So the picture in this case would be, okay, so for the standard Gaussian, so I should maybe explain the picture. So this picture is in complex dimension 2. So you have two variables, Z1 and Z2. So here, it's not possible to draw with one picture because C2 is 4-dimensional. So this axis here represents the modulus of first variable, and this is the modulus of the second variable. And the second one here is the argument of the first variable, argument of the second variable. Now, if the zeros are accumulating around the unit circle, unit torus, what you expect to see is that the modulus of Z1 and Z2 should be close to 1. So that means that the zeros should accumulate around 1, comma 1 here. And also if they're uniformly distributed around the torus, then the arguments should be uniformly distributed in minus pi pi and minus pi pi, right? And that's what you see for the standard Gaussian. The picture for other random variables, when AJs are not standard Gaussian, but some other random variables. Now, if you remember in dimension 1, the pictures were similar, but here in higher dimensions, we see quite different pictures. I don't know if this reflected, but like, I don't see any zeros here. And there are some clampings and, like they come together, but this one is more like, separate. I don't know. Well, one reason is that in dimension one, there is a local universality result. And that is due to Tao and Wu, Terry Tao and Van Wu. So what this tells you that in dimension one, the correlation functions for the zeros of random polynomials for, say, some Gaussian and some AJs, like maybe Bernoulli, are sort of asymptotic. That means that the difference somehow goes to zero. So that when you look at the pictures, the local pictures are quite similar for random variables that have the same, say, expectation variance. I think maybe up to moment 2 or moment 3, I'm not sure, but when you have two random variables that match up to some order of moments, you see the same local pictures when you draw the zeros of random polynomials. But in higher dimensions, we don't have such results, at least that I don't know. There is a theorem like that. And such pictures also say that it might be otherwise. So we don't know. Okay. But what I'm trying to say here, even if you have the theorem that the zeros are converging weakly in the sense of measures like this, the local pictures might not be similar. Okay. And then the other model, the ball model, where you take your K to be the unit ball in cm, then the equilibrium measure becomes the normalized surface area measure on the unit sphere. This time you obtain the scaled monomials, and the scaling constant comes from the L2 product like this. And your random polynomials are of this form. This time, this constant pops up. And when you play the same game, you see that in the Gaussian case, zeros are uniformly distributed with respect to the surface area measure. You see, in dimension 2, you can denote the sphere as, okay, so mod z square plus mod z1 square mod z2 square has to be equal to 1. So this is the boundary of the sphere in this picture. And the zeros are, these are the arguments of the zeros. And the same sort of experiment done for a different random variable. And then this is the picture that comes up. Okay. Now we can move on to geometric universality. So, okay, so what is the context? Maybe we should explain this a little bit. So you start, so in this case, AJs are all standard complex Gaussian with mean 0, variance 1. And random polynomials are, when the random polynomials are in this form, so this is the Katz ensemble, you look at the normalized fluctuations. So here you have a test function, psi. You're assuming some smoothness. Okay, so here it's assumed to be C3. And then you act on, so this is just the sum of the values of psi on the zeros of Fn. And then you subtract the expectation and you divide by the square root of the variance. So this is very typical. Now this is a random variable with mean 0. And because of this, its variance is 1. Now, what the theorem says, this goes back to Sodin and Strauss-Ohn, that this random variable converge in distribution to the standard Gaussian as n goes to infinity. Later on, earlier, there were some results that goes back to Maslova when under different conditions, of course. So I think when the coefficients are IID, their mean is 0 with 2 plus epsilon finite moment. But this paper of Sodin and Strauss-Ohn treats two different models as well, not only Koch ensemble. So it's more recent, and I think they treat the Weil ensemble. They also treat the elliptic ensemble and obtain the same result for those models as well. Whereas this was only for Koch ensemble. Okay. Now, so we want to sort of prove a similar theorem like this. So so in our setting, what we do is this. Okay. Now, say you choose these random polynomials f1 through fk. They all have the same degree, and you choose them independently. Now you have k of them. So if you look at the simultaneous zeros of k of them, this is a codimension k complex variety. Okay, of course, for generic f1 through fk. Now, when you have a kk test form, you can integrate this form over this variety. So you give me a nice form, and then I integrate and then subtract the mean. So mean is just taking the average of this with respect to my product probability measure. And then divide by the square root of the variance. So this becomes a random variable of mean 0 and variance 1. Now, the question is that normalized linear statistics, the question is, are they asymptotic to the Gaussian, like in dimension 1, in the case of Sodin and Strauss? That's the question. But in order to explain the result, we need some terminology. Remember, I was choosing a k and a weight function to define my inner product. Here, I take k to be the all of Cm. And in order to define the product, in the inner product, I take phi to be a C2 function. I need some smoothness. I need such growth condition so that all polynomials are R2 integrable with respect to this. Okay, so I have an L2 product like in the earlier case, and I have this L2 norm, induced L2 norm here. Now, in this setting, so some addition, this has not been defined. Again, for this setting, k to be Cm and phi to be this function, you have a vk phi, the extremal function vk phi. And there is a set called bulk. So the bulk is defined as the set of all points in Cm, where this phi coincides with my function vk phi, and where phi has positive curvature. Okay, so this is a C2 function. So this is a 1-1 form. I look at all the points where this 1-1 form is a positive form near that Z. So when I take the collection of all such points, I call it bulk. Like one example here is that if you take phi to be mod Z square over 2, then the bulk becomes just the unit pole itself. So maybe a few words here in connection with the global universality result. One can prove that in such setting, the zeros of complex random polynomials accumulate in the bulk or near the bulk. Okay, so you expect that everything is sort of accumulating around the bulk, and now you take a m-1 m-1 form, which you can integrate over 0 locus of a random polynomial. I'm assuming that this form has C3 coefficients, so it's smooth enough. Okay, just take a test form, C infinity, that's enough for me. And assume that this dd bar of phi is non-zero. So this makes sure that this random variable is not constant. Okay, because if dd bar is 0, then by integration by parts, this becomes 0, and then you just get the 0 variable. So that just ensures that. And it says supported in the bulk. The reason is that because the zeros are accumulating in the bulk. Okay, then the linear statistics, now this time on the previous page, there's only one 0 locus here, F1. Okay, then this thing converges in distribution to the real Gaussian. So I said this is a geometric universality. The reason is that you see the limiting object is independent of the choice of the weight function phi. So the weight function phi somehow defines geometry, the metric on your space, and the limiting distribution does not depend on that. Okay, so maybe a few words about the proof, because we don't have much time. So the idea is to use this cumulant method. Remember, for a random variable Z, you define the cumulants to be just a log of the expectation e to the tz. on the right-hand side, these are the cumulants. And the classical result tells you that the random variable z is Gaussian if and only if these are 0 for all k's except for 1 and 2. Okay, the first one is the mean, the second one is the variance. Well, in my case, because I use normalized random variables, the mean is 0, variance is 1. So I know what these numbers C1 and C2 are. And now the argument in Solin and Strasson gives you that gives you a way of estimating the cumulants in terms of the near and off diagonal asymptotics of the Bergman kernel. Okay, so this was a probabilistic argument, and here it was translated into a complex geometric argument. So this is the asymptotics you need, basically. So if you look at this is the Bergman kernel, just like in dimension 1, in higher dimensions you define the same way, but you have the weight here, phi. So if you look at the diagonal asymptotics Bergman kernel, it behaves like this Mongean pair, basically, of the phi in the bulk, and this converges is uniform in the bulk. And you also have this off-diagonal asymptotics. When these z and w are far away, the Bergman kernel decays exponentially fast. That tells you this. And again, when z and w are chosen in the bulk. Of course, this has been studied in many contexts. I think the first results go back to Tian, Kathleen, and Zeldich for the diagonal asymptotics, or the first order asymptotics of the Bergman kernel associated with positive line bundles. Later on, Schiffman and Zeldich off diagonal asymptotics. And then more recently, Berman studied big line bundles with smooth matrix, I think. Okay, so this was all I wanted to say. Well, thanks for listening. And if you have any questions, I'd be happy to answer.
Thanks a lot, Turgay. First, I think before I forget, I will ask people to unmute themselves and give a round of applause to Turgay.
Thank you.
And okay, now if anybody has any questions,